Well, thank you everyone for joining. Pleasure to have people come to listen to my talk today. I want to talk to you about element-based Galerkin methods for weather, climate, and ocean, as Sarah said. And I call it part two because, let's see, is it going? There we go. I call it part two because part one, I gave it back in October of 2024 to the same group. And that part was, I focus on, I hope you can see my very small spotlight, but I focus on non-hydrostatic atmospheric models and hydrostatic ocean models, kind of like what I'm going to do today. But I really spent most of my time on talking about the horizontally explicit, vertically implicit time integration methods. We had just published a paper on that work. And then we showed results for tropical cyclone rapid intensification using the NUMA model. And then I showed some results of one of our collaborators who's now at Florida State University. That was his PhD work, Yao Gahanzu, on this H-NUMA, which is we started off with our NUMA model, and then that group at Boise State and then Florida State added capabilities to do hydrostatic ocean modeling. And both of these models are written in modern Fortran. And NUMA is GPU capable, H-NUMO is MPI. Summary part two is this. So the difference is that I still will talk about these non-hydrostatic atmospheric models, and I will mention new work on hydrostatic ocean models, also based on these Galerkin methods. And I'll discuss entropy-stable discontinuous Galerkin methods, in particular for both atmosphere and ocean. I'll show some results for space weather applications, which is a new line of work for us, and we've been helping the Naval Research Lab in DC and Monterey extend their global operational models to be space weather capable. And also we'll talk about GPU performance of our entropy-stable DG codes. There's a paper that we're writing as we speak. And I'll show you some preliminary ocean modeling work on these entropy-stable methods. And the entropy-stable DG codes are written in Julia. Okay, so acknowledgements. The NUMA model, it's been in development for years. I think it's kind of come to the end of the line, so to speak, because the model that we used NUMA as a prototype to build the Navy's operational weather system, and that system has now gone operational in terrestrial weather, and it should go operational for space weather next year. And that work is, I have, not enough room to put all the collaborators, but it's basically, I always say NUMA was built on postdocs, right? We had over 13 postdocs in more than 10 years developing the model. And so a big thanks to all of them. NUMA is also part of the NVIDIA SDK testing analysis suite. It's run across various hardware, and we get to learn whether our model breaks when there's a new compiler option, for example. The entropy-stable DG atmospheric model, that was work funded. Oh, I should have said that the NUMA model was funded by ONR primarily, but we had DARPA money, NSF, and Air Force money as well. But it really has been a fully ONR-backed project for the most part. The entropy-stable DG model was previously funded by NSF and Schmidt Sciences, and collaborators is Henry Waterhouse, who's in this talk, listening to this talk here. And then we have Maciek Wadrzewski, he was a postdoc here. He's now at Sandia National Lab. Lucas Wilcox, MPS, Tim Warburton at Virginia Tech. And you can find the code base here for the most part. And then there's a new model that Henry Waterhouse is developing that is this ocean code, hydrostatic ocean code. The repo is private right now, but once we submit the first paper, it will be open as a public repo. And that is part of Henry's PhD thesis. So let me just give you a kind of a brief background in weather, right? For those of you that, it might be very basic for many of you, but for those that are not working in this area, it's kind of useful to learn the different regimes that we talk about, right? So for example, this big sphere on the top left corner here. So I'm drawing a sphere, and there's a lot of information here, but what I'm trying to get at is that The problem is difficult for a variety of reasons, right? The first one is that you have essentially, well, you want to be able to capture everything that's going on in the planet, but you also have scales, different scales, right? So, for example, if you look at this little red square here, right, that's what I call a horizontal grid. And the grid resolutions that are used for climate are on the range of 10 to 100 kilometers between those that delta, I call it delta H for horizontal, whereas the vertical direction, which is like this red, sorry, my Teams guy's coming up. There you go. Sorry, my Zoom window's coming up and blocking me from actually seeing what I want to show you. So this red square here in this direction radially, right? That's what I'm calling a vertical grid. And that really is way more resolved than say the horizontal, right? So anywhere between 250 meters if for the vertical resolution versus 10 to 100 kilometers for a weather model at 10 kilometers and climate models at 100 kilometers, right? I know now you have climate models that are really closing the gap on resolution with around the same range as weather prediction models. I don't want to talk about cloud resolving because I won't talk about that today, but we can think also of having obviously models that are embedded inside of general circulation models to be able to do, for example, hurricane simulations. And that was the topic of the part one. And I talked about the LES scales that you need to capture to resolve, for example, rapid intensification of hurricanes. But again, that's I'll stop there on that. I'll stop there. But the interesting thing, though, in the vertical direction, right? The resolution is finer than the horizontal, and it really is a special direction, right? Because most of the quote unquote physics occurs along that direction, right? For example, moist processes that creates clouds, and we worry about rain and inundations of because caused by hurricanes, et cetera. So it's very, very interesting to treat that direction differently. Okay, let's talk about the governing equations. Here's one form of the equations that we use in NUMA. And this equation here, this is your conservation of mass, this is your momentum, and this is your total energy. And we have in NUMA, we have about 5 different forms of the governing equations, and I'll explain why we do that, right? But this is one form. This is the typical one you see in CFD, for example. For space weather, though, you have to be very careful, right? Because you have to make sure that the equations that you use are valid under variable composition atmospheres, meaning that the gas constant changes, your gas constants change, right? They're functions of space and time, for example. And I can't obviously go through all of the stuff here today, but we do have about a 900-page DARPA report where we gather all the results of that 3-year project that was funded by DARPA. But I'll summarize 2 of the papers that are coming out of that work, right? And in this talk here. We also have in the work that I'll present today on space weather, I'll show you 2 other equation sets that we use to simulate space weather. And so this is another one, right? The same conservation of mass equation. Now the momentum is not in conservative form. And then we have here, little e is internal energy. So that's another form that we have. And there are some funny things going on here. And the reason why this looks so odd is because if you start from the first law of thermodynamics and you back out what the thermodynamic variable should be, if you want to use internal energy, this is exactly the form that you need if you want to have equation 1 in conservation form, so that you can prove things like conservation of mass, for example, in a classical Galerkin method. And that's why we need this form in this the thermodynamic equation in this form. And then you need an equation of state, for example. So this is what we call the internal energy form of the governing equations. But then there's another form that are known as the hybrid virtual potential temperature. So that's theta, and HV is for hybrid virtual. And the nice thing about that equation set is that the equations that are used in Neptune operationally actually use potential temperature as their variable, and well, in their case, it's moist virtual potential temperature. But you can also play a similar game by absorbing the gas constants and other things into this variable called theta HV. And I won't talk too much about it, but it does make extending a terrestrial weather model that's based on potential temperature to go to space weather, where you have things like variable gas constants, fairly easy to do. And we wanted to test this equation set. This is an equation that actually was published by Eckermann and colleagues at NRLBC back in 2023. Okay. One of the things that you see when you go up to space weather is that as you extend high, reaching the exobase, that density basically becomes very, very small, like 10 to the minus 15 is what the values that you get, right? So when you have things like division by density, that becomes problematic. Moreover, pressure also gets very, very small, and it gets exponentially small, right? So doing things like taking gradients of the temperature when you're representing it by polynomials becomes problematic. And what we've done here in the last few years is find workarounds, right? And obviously, one idea would be to bring in logarithms whenever you can, because now you have a simple way of representing exponential functions, right, as logarithms with polynomials. So this is what I'm showing you here. So basically, the equation 3 has the equation of state for the hybrid virtual potential temperature. The second one here is for total energy, and the third one here is for internal energy. And then based on that, you can treat this pressure gradient term in these 3 different ways, right? And it turns out that the one for HVPT and total energy is in a paper that's it's being prepared now by one of my former postdocs. And the one for internal energy has already been published in the work by Kelly et al. Back in January 2026. So that's kind of, in a nutshell, what we're doing to try to resolve these issues of things vanishing very quickly as you go really high up. And I'll show you a simulation to show you that, to kind of like hit you over the head with that concept, with that idea. We represent or approximate our spatial derivatives using element-based Galerkin methods. And for those of you that, well, I'm sure this is common knowledge, but I'll just go through it anyway. You have let's say you want to represent some PDE on some domain, omega. Then you divide it up into smaller elements or cells, omega sub e. And then inside of each of these subcells or elements, then you can represent your solution by some polynomial representation, for example, right? Here we use Legendre-Gauss-Lobato points to construct Lagrange polynomials on those points because they're good for interpolation and integration. And then once we have those basis functions, which I show you 2 examples of a function, for example, for a bicubic Lagrange polynomial defined at LGL points, then you can see that this guy here is the function for this point here in this box here, and this polynomial here is the one defined for this point here. And of course, the functions have this, they're cardinal functions, right? So they're 1 at the point that they're defined and 0 at the other points, but of course, between them, they vary. And then once you have these functions, then you can say things like, okay, now I know how to represent this variable, well, Q. This is the one on the left here means that I'm constructing an nth degree approximation of my solution variable Q. And I then expand the basis function for all points in that element, right? And then I can now, the Q sub j's are the actual variables of the solutions of Q, or the values of Q at those LGL points. But now I can represent my solution anywhere in that domain, right? Anywhere in that element, not just at the grid points. Okay, and then we start with our governing equations in continuous form. We then use our approximation that I showed you for expanding your solution variable Q. you plug it into your flux, for example, on your source function, and you plug these two back into the continuous equation, and then you end up getting a residual because this is a finite dimensional expansion, so you're not going to get zero, you're going to get some epsilon, right? So this becomes like a least squares problem. I want to solve I know that I'm going to look for a lower dimensional solution to this higher dimensional problem. How do I do that? Well, I make sure that the lower dimensional solution is orthogonal to the error. And so that means I multiply the error by a test function, which is that lower dimensional space. And I'm looking for that these two spaces are orthogonal. And there it is. So that's your finite element statement. I won't go into these, but if you want to know something more about this, what I mean here is that you're looking for a solution Q that lives in some space, right? In this case here, I say, well, we have two spaces in our models. We either use a continuous Galerkin method that lives in H1, and they're all polynomials of degree n. And then there's a DG space that lives in L2, but again, we use the same polynomial degrees. So this makes it easier for us, or makes it easy for us to construct a single code base that has both continuous Galerkin and discontinuous Galerkin methods. In fact, in our models, we treat them the same, right? There's just the construction of the global assembly, if you will, is very different for both, right? But everything else is the same. We still use fluxes for all of them. Okay, the other thing that I want to talk about is these entropy-stable methods, right? They've become very popular in the last, 5, 6 years or so, maybe longer. And the idea of entropy-stable methods is that the Achilles heel, if you will, of these high-order methods are twofold, right? One is the fact that when you use high polynomial degree, people had issues stabilizing the problems, particularly for hyperbolic problems. And the other one is time stepping, right? You have non-uniform spacing of your Lobato points or whatever points you're using to construct your solutions and your quadrature formulas, and therefore you had small time steps, right? So those are the two things that have been basically we've been trying to resolve in higher order methods. The time stepping issue can be resolved by implicit methods. That was kind of part of my part one talk about these, horizontal, explicit, vertical, implicit methods. We can I mentioned that in the vertical direction, the resolution is very fine. Well, if you do that fully implicitly, then you've solved that problem, if you will. For the spatial problem of having, for example, instabilities of high order, these entropy stable methods have been great. Now, it's not the only way to fix it, right? People have been using all sorts of regularizations like hyperdiffusion, et cetera, but this is another approach. And so let's go through it. Let's say you start with the conservation law. And then in the standard DG method, what you do is you do integration by parts on this term here, so the divergence of your flux. And here I'm showing you when you do integration by parts twice. So the way this discrete form of this continuous form looks is you have a mass matrix, and I'm assuming that the mass matrix is diagonal because I'm using co-located interpolation and integration like we normally do in spectral element methods, for example, or discontinuous spectral elements. We have a differentiation matrix here that operates on the flux F. And then we have from the integration by parts, you get from divergence theorem, right? You get a flux term, right? And this flux term, that's what I'm calling capital F, is that flux matrix that is kind of like a mass matrix, but on the boundaries of each element cell. And here, little f star is the numerical flux that you need to resolve the inconsistency, if you will, when you're at an element edge and you have discontinuous solutions on both sides of the edge because the different elements have different values. You have to resolve it in some way. Well, that's just kind of another way of doing a method of characteristics. That's called a Riemann solver, and that's what this comes from here. And this is the typical numerical flux that you get at each element E, right? So E, the superscript E is just an element, right? And then the difference between the standard discontinuous Galerkin method and then what is known as this entropy-stable DG method is that you rewrite this in a way that the actual flux values are modified, right? And so the flux is modified in this term here, which we call the volume flux term, because this requires a full integral inside the entire element. whereas the flux term or the surface integral term, right, is only the boundaries of the element, right? So this one here is a volume integral. So you need to come up with a new flux, and I'll tell you how we do that. And that new flux is also then used in the surface flux, but with some dissipation included. And that's what I mean by F star here. So for example, if you're thinking about constructing a kinetic energy preserving method, then the flux would look something like this. It would be just 2 times the mean of the velocity times the mean of some q, right? And if you wanted to then use that to construct the Riemann the Riemann solver, then you would add some dissipation term where this is kind of like if you know what a rho Riemann solver is, it's very similar, right? You have some matrix, right, which is just an eigenvalue decomposition, if you will, of your Jacobian operator, and this is a jump in some variable. In this case here, beta are the entropy variables, right? So let me talk a little bit about what I mean by those entropy variables here. So the way you do this is, imagine if you wanted to solve this conservation law. Well, then the first thing we do is we seek an entropy function, capital U, and then introduce entropy variables, right? So you take some differentiation of the entropy function with the solution variable U, and then you now construct a new representation of the original conservation law that looks something like this. Using the chain rule and simplifying, you now get this from, say, a system of equations that you started off with. You come down here and you end up with a single scale of PDE, that is your entropy, the governing equation for that entropy variable associated with your governing equations of motion of that problem that you're solving. And we now say, and this entropy function, by the way, is always chosen to be a negative, right? So you can say things like, okay, the function needs to be bounded. So I can say things like this, the solution of this equation should be less than or equal to 0. If it's 0, then we have entropy conserving methods. If it's less than 0, then we have an entropy dissipative or entropy stable method, right? And once we know what this flux should be, then we track back and figure out what that flux of the original PDE should have been. And that's kind of it, right? That's really the bottom line. Okay, so based on that, let me show you some results. I have about, on my 27 minutes, it says. Okay, that's a lot of time. So maybe I went a little quickly so far, so apologies if I went too quick. Space weather, let me talk about some of these results, and then I'll show you some results for the Galerkin stability in a 3D channel. I'll explain to you what I mean by that. We then will discuss work that my student Henry Waterhouse has been doing on the GPU performance of this entropy stable DG code. And then we'll talk about some, really preliminary work that we're doing, or Henry's doing, on ocean modeling, right? So it's basically, how do we construct the entropy stable DG ocean models, and that is GPU capable and other things. Okay, so let me explain to you this problem. There's a lot to explain here. Okay, hopefully you can see my pointer. So the thermosphere, right, for space weather, right? Well, maybe I'll start with this diagram here on the right. Here's what we want to do. We want to get to about, so this is about 150 kilometer altitude. Most weather models are roughly in the range of like 30 to 50, certainly below 60 kilometers up high. And to do space weather, you want to get to actually to 500 is where we want to get to, right? 500 kilometers. So I'll show you some results today at 300 and then 200 as well. But the important thing is you can see how the temperature profiles vary, right? So here at the surface, we're about 300 or so Kelvin. There's an inversion layer, there's another one, and then you see now once you start getting really high up, it starts going up because you're obviously very close to the sun, right? You're getting closer to the sun. And then the blue line, the density, shows you that, and the scale of densities up here, right? So here's it's about order 1 at the surface for density of air. And then as you go up to about 150 kilometers, let's say it's up about 10 to the minus 9. And when you get to about 300, it's tiny. And in fact, you'll see that here. You can actually see it here in this example here. Yeah, it's about 10 to the minus 15 at about 300 kilometers. So that's problematic, right? Because I said before that you have things like, either one over rho, whether you have a non-conserved form of the equations, or you have one over rho and somewhere, because you're even from the conserved form of the equations, you're trying to extract a primitive variable for u, for little u, for example, that you're dividing big U by rho. So there's all these problems that come up. But anyway, so the thermosphere extends from the mesosphere, which is about here, so about 85 kilometers, and then it goes all the way up to beyond the exobase, which I don't show in this diagram here. And the problem with, well, once you get up to the exobase, then the continuum hypothesis falls apart, right? But up to there, we can still use this continuum hypothesis and use these equations. Thermosphere is characterized by high temperatures, low densities, and variable composition. That's the other problem that you have to resolve, is that you have things like gas constants are changing, right? There's molecular diffusion. There's all kinds of stuff, right? You have diatomic gases that you have to really be mindful of. And they change with the diurnal cycle of the planet, right? Whether there's sun or night. And the ionosphere, which is inside the thermosphere here, right, is a charged layer that affects lots of different things, right? And so that's really, really important for satellites, for all kinds of things. We have tons of satellites in space now. And it's really affected by, heating of the sun, but also by terrestrial weather. So that's where kind of both ends meet, if you will. So that becomes a very, very special and tricky place to resolve. Ionosphere is also sensitive to signals from the surface of the planet, right? So it's really easy to pick up signals up high. So for example, if you have volcanoes or earthquakes, and I'm going to show you now in a minute, these gravity waves that I'm doing below in the simulations, you see that they attenuate as they go up high, and they get very, very strong up in this area. So here's an example of 1D propagation of acoustic wave, right? So it starts at height of 5 kilometers. This is a paper by Griffin and Thuburn, Quarterly Journal, 2018. And so let's look at this bottom left figure here. The first panel is the vertical velocity W, and the second panel is the density. And I just show you the density is not changing, right? But I'm just showing you the scale a little bit, right? But I'm just showing you what the scales look like. So you start at about order 1 for density at the surface, and it goes up to about 10 to the minus 10, let's say, at 200 kilometers. And you can see that this initial, let's wait till it goes back to 0 here. You can see that when you get to this starts at some very, very small bump in velocity, and it gets very, very large very quickly, right? We start at some very small value, and it's hitting between plus and minus 50 meters per second. Here we go, same exact problem. Now we just go up to 300 kilometers. You can see that it gets even worse, right? So first the density goes up to 10 to the minus 15. Oh, it goes down to 10 to the minus 15, I should say. And then you can see that now these velocities are going larger than 50, plus or minus 50 meters per second from that initial small velocity at 5 kilometers. And this is that signal that I'm talking about. And you can see that in gravity waves, flowing over mountains, for example. I'll show you some of that actually in the next slide. Okay, so here it is. So this is a 2 slides, sorry, 2 figures, and this is basically the whole paper that we are writing, right? And let me just walk you through all the stuff in here. So this is actually a simulation of a full planet, the whole 3D planet. And what I'm showing you in these slides here is, in these figures here, is just a slice of the longitude direction, right, in the horizontal, and the height or altitude in the vertical direction. And it's taken at the equator. And the nice thing about the simulation that we've been doing with NUMA is that we're able to make we're able to change like the radius of the planet very easily, and obviously the rotation of the planet. And we do that because when you do this, it becomes, you can actually get the steady state quicker when you reduce the radius of the planet. You're just basically making this thing spin very quickly. And then you get your steady state problem a lot quicker. Otherwise, this simulation would take days and days and days, and it'd be very expensive to do. Here, the simulation takes about 60 simulation hours to be able to get this kind of steady state solution. And what we're doing here is right at the bottom here, at about 50 longitude, there's a mountain, very small mountain. And then we just have a 20 meter per second flow that we push across the manifold of the sphere. And then this will eventually develop these mountain waves, gravity waves. And there's a lot of stuff that goes in here. You need to have these very sophisticated non-reflecting boundary conditions up top to be able to get this simulation to work well. And what we do here is I actually have all of the three equations that I talked about, right? The one that used total energy, the hybrid virtual potential temperature, and also the internal energy. Those are the three equations that had the different thermodynamic variables, and they're all listed here, and they all look pretty much the same, right? The one that's the outlier is the total energy one. So that's the SIAM curve, right? So that's the total energy. The black and the red are the other two. And we see this over and over again, and we're still trying to figure out why that is. We have some conjectures, but we have to confirm them. But they're still pretty close, right? They're pretty close. If you look at all these contours, they're pretty similar. Now, the other result I have here below is the exact same test case, but now we're using variable composition. So we let first of all, there's a non-isothermal profile in the atmosphere that is consistent with the variable composition of the atmosphere, and then we have the gas constant change as well, and that's based on data that's collected, observational data. And then what we did is we ended up just constructing a smooth representation of that data so our model doesn't complain about there's some discontinuity in your gas constant, right? And when you do this, now you see that the curves are different, right? And then you can see it primarily in the scale. So here, and by the way, I should have said that this is plotting the vertical velocity. So this going from minus 0.6 to 0.3, and then minus 0.35 to 0.15. So it's basically an order of magnitude smaller when you do variable composition, and that is in good agreement with what has been seen in the atmosphere, and also with a previous paper that we published on the Neptune model that used a different equation set, and that's in the JCP 2026. It was just published, or it appeared January 2026. So good agreement across the three versions of the equation sets in NUMA versus Neptune. And then we see that even between the constant composition and the variable composition, there are differences, and we expect, of course, to see those differences. If you don't use variable composition, you're making a lot of mistakes in the simulations, right? You won't capture the space weather properly, and you can see here in this simple example that you'll be off by a factor of 2 in your vertical velocities, right? But yes, there's more to come. We are still working on this paper, but hopefully we'll have it done by the end of the year. Okay, so up to this point, I've been talking about NUMA, which is a modern Fortran code. I said that that's pretty much, we're not really doing a whole lot more development in that code base anymore. Next, I want to talk to you about our Julia codes that are entropy-stable codes. And so this is an example this is a 3D simulation, right? So full 3D simulation of what's known as a baroclick instability in a channel. And you can see the scales, right? In the x directions from 0 to 40,000 kilometers, right? And so this is a problem, even though it's in a channel, it's trying to mimic the same range of scales that you have in the full planet. In the y direction, it's from 0 to 6,000 kilometers, so that's a little smaller there, right? But and then you have you're not seeing it, but coming out of the paper, that's the z-axis, right? That is, I believe, for this problem, is 30 kilometers is the model top. And so what I'm showing you here is just a slice at z equals 500 meters to show you after a 12-day simulation what happens. And the first row in the top here are the pressure curves, and then the second row are temperatures after 12 days. And I chose 12 days because that's what is shown in the original paper that showed this test case, and they compared against other models, and that's what they showed us. So I want to do the same so you can be apples to apples, right? And the difference between the first column and the second column is that the first column is the new entropy stable DG Julia code, And the second column is NUMA, using all kind of all its capability, right? So using the tensor viscosity hyperdiffusion operators that we have in it, the heavy time integrators, all that stuff. It's using a lot of machinery. It's using continuous Galerkin methods in this simulation here, but we've also done it with our entropy stable version inside there, and we get similar results. But I want to show you like, this more mature model on the right and this new model on the left. And the nice thing about the entropy stable DG code is that it doesn't use any diffusion at all, right? It's well, not additional diffusion. Whatever diffusion that is in there is in this dissipation in the numerical flux, for example. And it's using fully explicit, Runge-Kutta methods, right? That's it. So it's not getting any extra dissipation from implicit solvers, et cetera. And the results look really good. Like they're really close, right? And we've done these tests to convince ourselves that the entropy stable DG code is doing exactly what it ought to be doing, which is great. And this is a paper that we use this for a GPU paper that we're writing. And next, I want to show you those results for how this entropy stable DG code behaves on a GPU. So on the left, you have a roofline plot on the A100. So all these runs were run on Delta at NCSA in Illinois. And what we show here is that, okay, so here's your memory bandwidth of the hardware, right? And here's your your peak performance of the hardware here. And this is a log plot, right? It's log in the vertical axis, right? And yes, okay, log and vertical. Okay, sorry, we have two plots of this, and I have to make sure it's not the linear one. And then we have different shapes, right? So you can see that a solid circle is polynomial degree 2, all the way to a pentagon that's degree 6, right? And then on the right axis here, this is the grid refinement. So what number you see here, it's basically 2 raised to that power, right? 2 to the 6th power of refinement per element, right? And so what we see is that obviously as you go to higher and higher refinement, so the yellow guys, you see that they get very, very close to the peak performance of the hardware. And we're getting about 70% of peak performance for our best kernels, which is this square here. This is n equals 3 and the triangle equals 4. You do see a shift to the right as you increase the polynomial degree. So when you go from 2 to 3, and then triangles are 4, diamonds are 5, where are the diamonds in here, and then there's pentagon 6, right? So you do see there is some shift, sometimes that goes left, but that's for, perhaps caching and other things, other issues, right? But anyway, so this is a paper that we are in the process of finishing up. We're almost done with it. So look for it in either archive or we'll post it on archive once we're done. On the right, we have just the share of GPU time, percent of it, for the 3 kernels that we really, that you can partition your algorithm into, right? So you have a volume flux, which is what this roofline plot is talking about only, right? So the volume kernels. You have the surface kernel, which is doing the Riemann solver at the edges of the elements. And that's the communication that the model has. And then you have the explicit time stepping update. And what you see is that when you have n equals 2, right, the surface kernel dominates. And as you move to higher and higher degree polynomial, not surprisingly, you start seeing that the volume kernels start to dominate the CPU, the wall clock time, right? And what you see is, anyway, and why that's important is because what we're showing here on the left is only for the volume kernel. And of course, we would expect the surface and RK updates to be more like memory bandwidth bound. And so we feel very good about this. And that led us to then look at, say, the multi-GPU scaling. And you can see that for this example here, the top plot here is the strong scaling that we have. We only went up to like 32 GPUs on that machine. The Delta has 400 of these A100 GPUs. You can see you start losing right away. You start losing the scalability because we're now no longer saturating the GPUs. And then if you look at weak scaling, so I have 2 scaling results, right? One is what I call the optimal graph partitioning, right? Where basically we're using this pforest library to do our graph partitioning. And every time you in this simulation here, there's basically a pforest tree in every one of these GPUs. So when you they have their own tree structure, so you can scale this problem to any number of GPUs. And for those that are not accustomed to seeing strong scaling and weak scaling, the strong scaling just means I leave the problem size fixed, right? And then I just I change the amount of hardware that I'm using. We've done this for our CPU codes like NUMA, and we get very good results like, 99% strong scaling for a big problem. But here, because of the GPU not being saturated, you lose that capability. On the other hand, in weak scaling, right, you want to have the amount of work done per device the same. So if I increase the number of GPUs by factor of 2, I'm also increasing the problem by a factor of 2. And so you see that you really get a really perfect looking weak scaling. The second plot on the right here is if you didn't have that perfect graph partition, that you basically started with one tree for the whole grid, and then you're ending up partitioning it across GPUs and dealing with that, right? And that's what you're seeing here, that your cost is increasing as you increase the number of GPUs. Okay. We also did some, not apples to apples, right? But the best way for us to see what is the difference between our GPU and CPU codes is we used the entropy-stable DG code as our GPU code, and we use NUMA that has both entropy-stable and classical continuous Galerkin methods as our CPU code, because we've benchmarked that across different hardware over the years. And what we see is we compare the GPU code on an A100, and this is the Milan that's the CPU that's on the Delta machine. And we compare devices here. So device for the A100 means GPUs. Device for the Milan, AMD Milan, means nodes, right? And I show you here what a node looks like. And this is the time to solution that you get between, say, going from 4 to 8 to 16 of these. And you see roughly about, well, let me just, here's the time to solution and the energy consumption in megajoules. And this is the ratio in time that we have between this 11.2 means that the A100 is 11 times faster than the CPU code, is what this means here. And this number here means that it's 15 times more energy efficient. Right. And you can see that as you increase the number of devices, there's a dip, but then increases again. So worst case scenario, I would say that for the simulation that we've done, the A100 is about factor of 10, or maybe saying a different way, our GPU code on an A100 is roughly a factor of 10 faster than our CPU code NUMA on the Milan core, and about 13 times more energy efficient. So that's what we have so far on that result. Let's see how much I got. About 6 minutes left. Okay, good. So ocean simulations. This is the last part of my talk. We've been developing an ocean model. So if you think about ocean models, one way of doing this is you can construct a shallow water model, and then you stack layers, right? And that you can construct a hydrostatic ocean code that way. And each of these layers are using what are known as isopycnal coordinates, right? So you have these constant layers of density, right? And our governing equations look like this. They look like the standard conservation of mass equation in shallow water, in a single layer shallow water code. That's this H here for the height of the layer. And then you have your momentum equation. And the momentum equation looks also very similar to a classical shallow water model with Coriolis. I could also add things like wind stresses, also add bottom friction, but I won't talk about that here. And then what makes it a multi-layer equation is really this first term on the right-hand side of the second equation, which has essentially things like the bathymetry B, which that would be in a shallow water model, but it's this sum across layers, right? So for example, this guy here would be, let's see, L greater than K. So, right, so it'd be from, let's say if you're this layer here, you're going from this layer all the way here. So that's basically, you're feeling the bottom shape of the of the layer is feeling what's below it, right? So it's almost like it's the bathymetry that you're feeling, right? As opposed to this guy here, that the densities, these are densities. So this is really feeling the weight. So this one here would be like, I'm in this layer here, and I'm feeling the weight of all the layers that are stacked above me. So there's two forces here at play, right? There's, I call this the bathymetry effect and the basically the weight. And so that's what the equations look like. And then we constructed a entropy stable version of this code. And the first thing we did a single layer Stommel problem, which why? Because we had done this before with a DG code years ago. Tim Warburton and I did this years ago. And then you can't tell that clearly, but maybe you can kind of, if you can squint, you can see that it's roughly the same solution, right? In fact, I bet if we did the contouring exactly like we did it in the right here, you'd see the same thing here. And that's something we need to do to make sure that we are comfortable. And we also have an analytic solution to this problem, so we haven't done that yet. But it was a good first test to do. So these are very preliminary results that I'm showing you here today. We also did a manufactured solution, right? So this is now a three-layer problem where you assume a trigonometric solution, heights, bathymetry, constant velocities, etc. Plug it into the governing equations, and you get a source term, and then you know what the solution is, and then you can show that you get a certain convergence rate, and we hit convergence pretty quickly at at 12 degree polynomials. We're getting almost very close to double precision. And this simulation, let's see if this runs. So this is what the simulation looks like. It's just a bunch of trig functions, moving around, right? So very pretty. So you can see the three layers here, layer 1, layer 2, and layer 3. And I'll let it finish out there. 3 minutes, okay. All right, and then we did a well-balanced test. And this is a test by Yao Gahanzu's paper that was published in 2026. And so what it is you start with a bottom, we add some bathymetry to the bottom layer, and you see if that causes any issues, right? I've done this before with, like, say, a classical C continuous Galerkin method, a classical DG method, and then entropy stable methods. And you'll see in the non-entropy conserving methods that are not well balanced, you'll see velocity start slowly growing, right? Whereas with the entropy stable DG that is well balanced, nothing happens, right? So it'll sit there forever, which is great. This is a different problem that we are now looking at. This is a way to check that your baroclinic waves are moving in the right speed. So this is just a simulation that I asked for Henry to do like a few days ago. He just sent me this plot, but now we have to check to see that we are getting the same results that we would expect from the paper below down here. But the point is, right now the code is fully stable, right? It doesn't seem to break, which is a good sign. We kind of went for broke and then try to run what's called a double jar problem. This is a big problem in ocean modeling. You start off with well, you can have bathymetry and stuff like that, but this has wind stresses, it has Coriolis, it has bottom friction, it has a lot of stuff. So it's like really like even though it's idealized, it's still very realistic as an ocean problem. And we ran the code with entropy stability. So here's the solution, what it looks like. I know it looks really ugly, right? But there's no viscosity. And we compare it against the Navy's ocean operational model called HICOM that has this artificial viscosity, and in the HNUMO code that has this artificial viscosity. And so there's no great match between HICOM and this other DG code, but we are seeing that we're getting some structures that look similar, but they're not the same, right? So I would say that the numbers of, like if you look at quantitatively, the contours are similar in size. So we feel that and these are like simulations that run for, I forget, like, 20 years, right? They're long simulations. And this is a fully explicit model with no viscosity, and it just runs, right? So this is very excited about these results. We still have some tweaking to do, but I think we're off on a good start. 43 seconds. So my closing remarks, we compared 3 equation sets for space weather and NUMA. 2 match closely the hybrid virtual potential energy. Sorry, it should be temperature, not energy, and internal energy, and total energy being the slight outlier. The agreement was close between all 3 equation sets for both constant and variable composition, but there are differences between variable and constant composition as we should expect. The entropy stable DG atmospheric code was shown to compare well with NUMA, I only showed you one result, but we've done other things like discontinuous bubbles in 3D, that kind of stuff. That'll be in the paper. Because these entropy stable DG methods are they use provably stable numerics, they don't require any hyperdiffusion for stability, which is great, right? You may still need it for some applications or maybe for cosmetic reasons. I can talk about more later if anyone's interested in that. But for space weather, we would need it, right? We need molecular viscosity, and that's something we have to add to our models if we're thinking about using it for space weather. But for terrestrial weather, you don't need it, right? We've done things like baroclinic instabilities on a full planet. We've done Held-Suarez test cases that are used in climate simulation without any dissipation at all, which is awesome. Element-based Galerkin methods are in atmospheric modeling are now well established. That's awesome. When we started years ago, that was not the case. Now there's two operational NWP models, one in Korea and now in the U.S. Navy, and a couple of climate models. The E3SM model uses spectral elements, and the CLIMA model, I wouldn't call it operational, but they're doing climate work with it, also use a Galerkin model. And we began this journey a few decades ago. I think the first paper I published in this area was back in like 2002, maybe. So yeah, it's been over 20 years. And we saw a big change in atmospheric modeling from being hydrostatic to fully non-hydrostatic, even for global modeling. We now have models that all they insist on conserving mass. They don't really use the shallow planet approximation as much, has moved over to the deep planet equations because without that, you can't do space weather. And NUMA was designed from the beginning to be deep planet capable. So I think we were one of the first models. There was a study done by NOAA years ago, and if you're interested in go look there, you'll see how NUMA stacked against other models that were being considered for the National Weather Service's next model. And then the last point I'll make is that element-based Galerkin methods and entropy-stable methods, can they make an impact in weather and ocean modeling in the future? We've seen that these methods have been, at least for the element-based Galerkin methods, they've been very useful already in the atmosphere. And I think that they're going to be more useful in some sense for the ocean because there you really need that capability to do, for example, coastlines, right, which require you to do unstructured grids. We already pay the price in all these simulations I showed you, and our models they're ready to be, they can do non-conforming adaptivity. We pay the price of having, indirect addressing as in unstructured grid models. But in the atmosphere, you don't really use any of that stuff, right? What you do is you basically just warp the bottom surface and you're done. So we pay all that price in our machinery already. In the ocean, I think we can take advantage of that very, very well. So I'm looking forward to seeing how these methods are embraced and used in years to come. And with that, I will stop. Thank you very much.
Thank you very much, Frank. Wow, what a what a journey. Quite a lot that you covered, but it was very clear, and I really appreciate it. Not being an atmospheric or ocean modeler, I do deep subsurface simulation. I definitely had a really great appreciation for
Thank you.
the the leaps that you have made over the past couple of decades. So for everybody else, please do put your questions in the chat. There's not very many of us, so I'm definitely more than happy to let people unmute themselves and ask questions. It's open now for discussion. So while we're waiting for people to think about their questions, as again, this is not my field, and a lot of what we do in the deep subsurface involves transport of various things, and I'm sure in the atmosphere and the ocean this is obviously relevant, pollution, particle transport, you name it. Help me understand how easy or harder it would be to include transport or couple it with transport or other kinds of, let's say, multiphysics. Here you have the complete package of energy and mass momentum. I'd love to hear
Yeah.
your thoughts there.
Oh, yeah. So yeah, in this talk, I didn't talk about any of that. And I'm trying to think, even in the talk back in part one, right? I presented work on, for example, moist simulations, right? You have hurricane
Right.
simulations, you need that in that. And we need to transport all kinds of moist variables. I think in the results I showed, I only had uh, just condensation, right? So I had basically clouds, rain, and just
Right.
water, right?
Of
But
course.
yes, for a full like, in fact, I would argue that NWP models and including climate models, what they really do is they just push species around, right? They
Right.
become transport models. They have, I think most operational models will have hundreds of species that they're pushing around. So that
Yeah.
becomes a huge part of the cost of the models.
Right.
And so the Neptune model that I talked about here briefly, they have lots of species, and they handle them using discontinuous Galerkin methods, for example. You got to be careful with obviously having positivity in your in your
Yeah.
variables and so forth. But yes, you do have to be very careful with that. I believe the E3SM model, they rely on semi-Lagrangian methods, right? Because that's kind of a nice way of doing things, right? You want to find you're at some grid point, you want to find what that grid point was previously, and once you do that, you resolve that departure point, if you will, then you know where all your traces were and then where
Mm.
they're going to be, right? So now you spend a lot of time getting that departure point properly, and then now you interpolate your fields or do something whatever to figure out what that all those species are going to be, the values that they're going to be at in the next
Yeah.
time out. So that's a very effective way of doing things, and
Yeah.
you can build things in like monotonicity, et cetera,
Right.
into
To
those.
ensure.
But yeah,
Mm.
it's a huge part of the cost, and that's having, for example, they tend to, well, they used to run transport schemes separately. Now, well, most models have to have them internally, right? You can't run them offline,
Internally.
right? But
Yeah.
yes, that's a big problem. I actually started my career in atmosphere working on transport schemes, and then eventually I moved over to the full governing equations and more focus on the dynamics, right? Of the dynamical
Right.
core, if you will, which is the
Right.
governing equations that I showed.
Yeah.
And yeah,
Exactly.
no, there's
Yeah.
everything, everything you've done, they come into this, and I'm sure there's like even in, the groundwater modeling, this, that, there's so many interconnections here that
Yeah.
I don't touch, right? But that you have
No.
to be mindful of those pieces.
Yeah, yeah, exactly. Yeah, thanks. Oh, there's a question for Jed Brown, one of the SIAM officers. Jed says, how was power measured when comparing CPU to GPU, or was that based on TDP,
Yeah,
ignoring
yeah,
the rest of the
yeah.
system? And maybe I don't know what TDP stands for, actually.
Thermal design power. Yeah, Jed,
Yeah, oh,
yeah,
yeah, yeah, yeah.
yeah. So right, we based it only on that. So thank you for pointing that out. And I would love to hear if you have a better way for me to actually get the energy that's being consumed by the hardware, right? Because yeah, we just based it on TDP. Exactly right. Correct.
Yeah. Uh, Energy being a hot topic these days, that would be an interesting comparison.
Yeah.
Yeah, let's see. Oh, here's one that popped up in the Q&A from an anonymous attendee. Why have you considered multiple layers with various density? Isn't it possible to consider density in a continuum approach and a thermodynamic property, the pressure and temperature dependence, and consider its variations in element scale?
Yeah,
Yeah,
that's a good question, and I will be, honest and say that I am not an ocean. I don't know a lot about the ocean, right? So the first thing we did, we just looked at what other papers that have been published in this area were, and we wanted to do as close as possible in apples to apples. I've learned from experience that when you are trying to build a new model and you think that you would like to offer it up as a replacement to an existing model, that you can't veer too far away from it, right? Because if you do that, then they're like, well, wait a minute, why did you do that? It's different. It's not apples to apples. So the first thing is useful to do is pick a model that you think you'd like to go, show the pros and cons of a numerical method and stick to the same governing
yeah,
equations. But yeah, all these other, I mean, the things that you're asking are basically things that are still on our drawing board. Like, what do we do
mm,
next? Like once we know that
mm,
we get the same results as this model that uses isopycnal coordinates, can we now go beyond that?
yeah,
And we are expecting to do that, right? But thank you for that.
yeah,
That's a good question.
yeah. Yeah, I mean, this is something that we experience also. We work with engineers, reservoir engineers, and we make a new code. And if you don't make it do it exactly what their code does with the finite difference or whatever it is, then they aren't going to listen. So I think it's really important that you have the stepwise approach,
Yeah,
Frank.
it
It's
takes longer.
common for everybody.
Yeah, it takes longer to do it, right? Because you like to basically leapfrog some existing technology, but that's very difficult to do. I think, I mean, I some of the people on this call, maybe from this, weather, climate, and ocean communities, and they see that for good reasons, right? This community tends to
Hmm.
be very conservative, right? You don't ever
Yeah.
want to be an outlier of a intermodal comparison, right? Even if it turns out to be you're an outlier for a good reason, and that's
Right.
why I mentioned that NOAA AVEC report. It turned out that why we were an outlier is because we were the only deep planet model in the competition. So we gave different results from others, and we got grief for it. And later
Interesting.
on, we resolved the issue, right? But so you have to be
Interesting.
careful being an outlier, right?
Yeah.
So you have to do things as close as possible to what's existing, and then start moving
Stepwise.
forward, which takes
Hmm.
longer. But at least you're getting people on your
On board.
side and convincing people.
Yeah.
Exactly. Yeah.
Exactly, exactly. Okay, I think we'll take one more question. We're about a few minutes over time here, but I think everybody will love to hear one more comment here. Thanks for the talk from Chris Vogel. Frank, I'm very interested in how ESDG methods can avoid hyperdiffusion, especially having had to personally juggling the time integration cost of hyperdiffusion, e.g. operator
Yeah.
splitting with substepping, et cetera, et cetera. Are there time integration considerations for ESDG, or can you, e.g., example, use the same Runge-Kutta scheme with the same time step size as the prior discretization? That was a long question, but
It
I think
was.
you
It's a
got the
good question.
gist.
I got it. Yeah, yeah. No, thanks, Chris. Yeah, no, I know Chris, and that's a good question. Yeah. In the work that we showed here today, we don't have any entropy stable time integration, but at the very bottom of this of my slide here, this Warzewski et al., we do use entropy stable time steppers. Now, admittedly, those are explicit, right? But you can do that. The In the work that we've done for like using these heavy time integration methods, the paper by I don't have it lit, I don't mention in this talk here, but it's by Souza et al. That was published in James in 2023. We use not entropy stable, but kinetic energy preserving schemes, and then we went through and built a heavy scheme based on that. So, but I still think you need to go through and prove that your time integrator is entropy stable. I mean, if you want to have a fully entropy stable method, you got to prove not just the time integration is entropy stable, the boundary conditions are entropy stable, everything's entropy stable, right? Does that matter at the end of the day that you need all that? I don't know. What our experience was that even by you just going to kinetic energy preserving schemes, which are way simpler, we never had to use hyperdiffusion, and we're able to do these Held-Schwarz test cases, right? We're able to do baroclinic instabilities. And for the atmosphere, unless you're doing like explosions and stuff like that, you probably, it may be the entropy stability is overkill, right? If you're doing hypersonics, you need it, right? So yeah, I would say that I would start with kinetic energy preserving. They're a lot cheaper. The fluxes are a lot cheaper. It's just basically just averages, right? As opposed to having logarithms and stuff like that, which is complicated and expensive. And I didn't say too much about that here, but that's kind of one of the values of running these ESDG methods on the GPU because the ESDG algorithms are so hungry for compute, right? And so you can
Mm.
feed the GPU with that because it wants a lot. It wants to do a lot of computation. And
Mm.
at the end of the day, right, if you're going to do hyperdiffusion and entropy stability, if you're doing fourth order diffusion, then ESDG is going to win. If you're doing second order, you might be a wash.
Mm. Yeah. Yeah. Good. Well, I hope that answered everybody's questions, and certainly was an interesting discussion. I think with that, I think we'll close this webinar. Frank, thank you very, very much for a really excellent talk.
My
Really
pleasure.
enjoyed it. And thank you everybody for listening. And of course, the recording will be posted on SIAM so we can share it wider. And with that, have a good rest of the day, evening, or night, wherever you may be. Thanks, everybody.
Thanks, everyone. Thanks for joining.